In this video, we will see PN junction under bias. So to start with, let me take PN junction under equilibrium, which we have been discussing so far, which is shown here. It has a depletion region, which we said is W, and its energy band diagram looks like this, where we assumed based on depletion approximation that the PN junction would have neutral regions, P neutral region, N neutral region, and we have a depletion region in the middle. We call this depletion region because it is depleted of mobile charge carriers. And of course, this region has immobile charge carriers, which are the dopant ions, which are fixed in the lattice, which cannot move. And there is electric field inside the PN junction, which is directed from N side to P side. Because of the electric field, we have drift current inside it, which is in this direction. Let us call this J drift. This is because of both electrons and holes movement. Now, at the same time, we have diffusion current, which is exactly in the opposite direction, which is this way. So that is J diffusion. As the PN junction is in equilibrium, the net current flowing through the PN junction would be zero. So as a result, the diffusion current and drift current cancel out each other exactly, where the Fermi energy level is constant throughout the PN junction. In the neutral P region, the whole concentration PP naught, the majority carrier concentration, is given by Na, which is the doping concentration itself, and the minority carrier concentration NP naught is given by Na square over Na. And on neutral N side, we have the electron concentration Nn naught, the majority carrier concentration given by Nd. Nd is doping concentration, and the minority carrier concentration Pn naught is given by Ni square over Nd. This PN junction under equilibrium had electric field in the depletion region, and there is a potential built up as well, which is called VBI, the built-in potential. But the bent over the energy band diagram is Q times VBI because the energy measurement is in electron volts for this energy band diagram. Now VBI is actually given by VT times ln of Nd Na over Ni square. And based on the relationships that we have here, we can rewrite this expression as VBI is equal to Vt times ln of Nd can be written as Nn naught, and Ni square over Na can be written as Np naught. So we can write this as over Np naught. And we can also write this as Vt ln of Nd by Ni square is actually 1 over Pn naught. So divided by Pn naught, and Na is nothing but Pp naught. We can rewrite this expression as Nn naught is equal to Np naught times e power Vbi over Vt. And we can also write this as Pp naught is equal to Pn naught times e power Vbi over Vt. Based on these equations, we can make a point that the potential across the junction would relate the carrier concentrations at the edge of the depletion region. And similarly here, the whole concentration relationships at the edge of the depletion region is related by the potential at the junction. And this is called the junction law, which we would be using in deriving the diode current equation. Let me take the same PN junction and apply potential difference across it. In order to apply potential difference, we need contacts. In the sense, we need to make metal contacts to this semiconductor on either side. And let's say this contact point is ohmic in nature. Now if you see this device basically has two terminals. So we can call this as a diode. Di representing 2 and ode represents terminals. Here we have two terminals so that we can call this as a diode. But in general, this is not any diode because this is very specific. This is a PN junction diode. Now we know before we apply the potential difference, that there is already electric field in the junction. And now let's say we are applying a potential difference. So let's say here we are applying positive and here we are applying negative. Let's say the voltage we are applying is V. And let me assume one thing, that whatever potential we are applying is going to directly get applied across the junction, the depletion region, not in the neutral regions. In that case, entire potential that we are applying is applied across the depletion region. But the potential is in such a way that this potential would establish an electric field in this direction. This is the electric field because of the applied potential. But let me also assume that the potential is very small in such a way that the net electric field is still in the direction of the built-in electric field. So now the resultant electric field would decrease. When the electric field in the depletion region decreases, the potential across the junction also decrease. As a result, the depletion width will also reduce. So let me reflect the depletion width reduction in this figure. Now let me represent the energy band diagram reflecting these changes. This is how it looks. Now we can relate this as in the junction the net electric field has decreased because of the applied potential, so that the slope of this bend of the energy band diagram would decrease. And so the potential across the junction would decrease. That's why this difference would be Q times VBI minus V. And this is exactly the voltage we applied, as we assumed that the entire applied electric field gets applied across the junction, not in the neutral regions. Now because of the applied potential, the potential across the depletion region has decreased. Now let us see what are the effects because of this. When the PN junction was under equilibrium, we had diffusion current and drift current exactly balancing out each other, so that we didn't have any net current flow. But now the electric field has reduced because of the applied potential at the junction. So as electric field decreased, the drift current would decrease, which means there is an imbalance between the drift current and diffusion current. So there would be a net current across the junction, and that would be diffusion current. And how do we understand the diffusion current in terms of energy band diagram? In equilibrium case, the barrier was too high for the electrons on the n side to actually surmount the barrier. Whereas when we applied the potential in this way, where positive to p side and negative to n side, the barrier has reduced. As a result, the electrons on n side now can actually surmount the barrier, which we will call it as the electrons injection into the p side. So basically electrons are high on n side, and we are talking about diffusion. These carriers would be injected through the depletion region onto the p side. And similarly, if you see that there would be holes on p side which are majority carriers, previously they were unable to go to the n side because there is a barrier built up, but now the barrier has reduced. As a result, the holes can surmount the barrier, which we are calling the holes majority carriers in p side getting injected through the depletion region onto the n side, so that the carriers, once they are injected into the n side, would diffuse through the n type material. And the exact details of how the carriers would move and all we will discuss in the next video while deriving the diode current equation. And we will discuss them in detail. Bottom line here is that because of the applied potential, there would be current flowing. And that current flowing is because of the majority carriers injected onto the other side. Once they are injected onto the other side, there they are minority carriers. So the carrier injection happens across the junction. As a result, we'll have some current flowing through the PN junction diode. And we also mentioned that electric field decreased, potential across the junction decreased. As a result, depletion width also decreased. So now let us see in terms of the equations how it reflects. We know in thermal equilibrium the depletion width was given by 2 epsilon naught epsilon r of VBI over Q times 1 over Na plus 1 over Nd whole power half. When we apply potential across the PN junction, the potential across the junction is not a VBI anymore. It is VBI in thermal equilibrium, but when we apply the potential across the PN junction, at the junction, the potential would be VBI minus V. Depletion width would be equal to 2 epsilon naught epsilon r VBI minus V over Q times 1 over Na plus 1 over Nd whole power half. Now we can see that VBI minus V would be smaller compared to VBI. As a result, the W under this applied potential difference across the PN junction would basically decrease. So now we can represent here that the depletion width would decrease because the electric field at the junction and the potential has decreased. Let me take the same PN junction diode, but this time let me apply potential in such a way that we are applying negative potential to P side and positive potential to N side, and the magnitude of potential that we are applying, let's say, is VR. This is exactly in the reverse direction compared to the previous case. When the PN junction was in thermal equilibrium, there was an internal electric field which was from N side to P side. But now because of the applied potential difference, we would have a electric field which would be in the same direction as that of the internal electric field. As a result, the electric field inside the junction would increase. And similarly, the potential across the depletion region would increase. So the depletion width would also increase. Let me reflect the depletion width increase in this figure. Now let me represent the energy band diagram reflecting these changes. This energy band diagram indicates the slope of EC has increased, which indicates that the electric field in the depletion region has increased. And that's what we discussed. And at the same time, we can see that the overall band of the energy band diagram would indicate Q times VBI plus VR. As the electric fields are in the same direction, the potential would get added up. So as a result, the overall band has increased, and the potential across the depletion region is basically VBI plus VR. The electric field would be present in this region. Where we have the depletion region, there is electric field in this region. Now if you compare to the equilibrium PN junction, where the drift and diffusion currents were cancelling out exactly at the junction, in this case, the electric field has increased, which means the barrier has increased. So the injection of carriers across the depletion region wouldn't be a case to consider, which means the diffusion current will not be a thing to consider. But the drift current would be considered because the electric field has increased. That's the only component we can consider. Now, how can drift current flow here? Based on what carriers? There are electrons which are minority carriers in P side, and we have holes which are minority carriers in N side. And because of the thermal energy present, these electrons and holes will be randomly moving in the crystal lattice. Now once, if they step into this region close to, then this electric field would pull this electron to the other side. As a result, this electron would find itself at the other side. And similarly, if hole comes into this region where the electric field is so high that this hole would be swept across the depletion region and it finds itself at the other side. Now if you see, there is a movement of carriers because of the electric field, which means it is drift current across the junction. This is the reason why there would be current flow in the reverse bias. But now, what is the quantity of this current flow? The minority carriers are very, very less, which means they're minute. Now the rate at which these are flowing, can you imagine the current? It would be very, very small. So this is a very negligible current that flows when we apply a potential like negative at P side and positive at N side. But now in terms of the depletion width, we can see clearly that depletion width has increased. So let me compare this with respect to the other two cases we considered. Depletion width would be 2 epsilon naught epsilon r times VBI plus VR. This is the voltage across the depletion region over Q times 1 by Na plus 1 by Nd whole power half. So it tells that as VBI plus VR is higher than VBI or VBI minus V, the depletion width would be higher in this case. The current flowing through the PN junction relation to the voltage applied across the PN junction is given by an equation which we would call the diode current equation, which is given by I is equal to I naught times e power of V over eta Vt minus 1, where we know Vt is thermal voltage, which is Kt over Q. At room temperature, this is 25.8 millivolts, and I naught is actually given by AQ dP Pn naught over Lp plus AQ dN Np naught over Ln. And of course, this looks pretty big compared to the overall current equation. Eta is actually called the ideality factor. In general, for germanium, it is 1. For silicon, it is 2. 1 being the most ideal, which means in an ideal diode current equation, basically eta would be 1. So if we take the PN junction like this, let's say this is P, this is N, and if we take a reference voltage as VD, that's the voltage applied across the diode, then we can call this V as VD. Then the current that would flow is, let's say, I, and that is this I. So the relationship between the current flowing through the diode to the applied potential across the PN junction is given by this relationship. Now let us see how this equation basically look graphically. This is how the characteristics would look like. When Vd is positive, let's say Vd is very small, in that case the fraction Vd over eta Vt, if it is small, then this overall value would be small. Once this Vd over eta Vt increases beyond 1 and a higher value, the exponential would come into picture where the current increases exponentially with respect to the potential that we apply across the diode. But assuming the Vd is positive. So that's why we have drawn in the first quadrant of this IV graph. Now coming to the case where Vd is negative. So here Vd is positive, and in this case Vd is negative. When Vd is negative, then this exponential, this term would be negative. Then the whole exponential would be a decaying function of the voltage applied. When Vd is less than minus 3 Vt, then this exponential is very close to 0, which means for minus 75 millivolts and below, this exponential term can be neglected. In that case, the current would be simply I naught. Let me represent that value here. This magnitude would be I naught. And it is surprising that this current is not depending on the voltage that we apply in reverse bias. And why is that? So if you go back and see on what we discussed, the current was flowing when we applied the potential as negative to P side and positive to N side because of minority carriers coming into this electric field zone, that this electric field was sweeping the carriers into the other side. How many carriers would come into this zone is not in the control of the electric field itself, which means it's not in the control of the voltage we applied. So basically the amount of carriers flowing wouldn't be in the control of electric field or the potential applied. As a result, the current would not depend on the potential that we apply. When Vd was positive, the current was flowing in this direction, whereas when Vd is negative, the current is flowing in opposite direction. That's why we represented the current in negative with respect to the reference that we took here, the I. And even the Vd, the reference was plus minus here. When Vd is negative, which means it will be opposite. And this I naught value practically would be very, very small. As we discussed, the current flow would be small in this case. This I naught value would be usually in microamperes or nanoamperes, whereas the current that flows when Vd is positive would be in few milliamperes. Comparing to this, we can basically neglect the current that is flowing when Vd is negative. When Vd is positive, this two-terminal device can be represented like this, where let's say this is anode, this is cathode, where I'm representing anode here and cathode here. Then when VD is positive, it basically allows the current to flow through it. So I'm just representing a triangle representing that current actually flows, which means the diode basically allows the current to flow, which means it is supporting the current to flow. Whereas when we go to the other side, where this is anode and this is cathode, when we apply negative to this and positive to this, it doesn't allow the current to flow. In general, it should be flowing from positive to negative. But in order to represent that current is not allowed through this device, we will put a vertical line indicating that it will not allow, it will oppose the current flow. As it is against when VD, as it is against the current flow when VD is negative, we will call this as a reverse bias. As it is biased in such a way, it is opposing the current flow through it. Whereas in this case where VD is positive, it is allowing it to flow. So it is forward biased, which means it is biased in such a way that it is allowing the current to flow. Now, in order to represent this PN junction, we can combine these two symbols and we can draw the symbol for PN junction, which would look like this. This is anode, this is cathode. And the voltage for reference is VD and the current is I, and the relationship is given by this equation, which is diode current equation. And now thinking about I naught, we get another question that can we increase the voltage VD negative as much as we want and the current would be constant? Well, not exactly. The reason why it won't be exactly that, we will discuss in a different video about the breakdowns. And this graph we have drawn is to just represent this equation. As we said, when VD is positive, the diode is forward biased. So the case where we discussed positive to P side and negative to N side is actually forward bias. And where VD is negative, according to reference, is this case where it is reverse biased, where this is for equilibrium case. And now in next video, we will discuss the currents flowing through the diode in detail, and we will derive this diode current equation by discussing all the necessary assumptions made in deriving this equation.